Let's look at the energy of an object as it moves in simple harmonic motion. As a mass on a spring goes through its cycle of oscillation on a frictionless surface, energy is transformed from potential to kinetic and back to potential. Energy is conserved, and here's the equation that describes that. Let's take a look at the diagram. When the object is at its maximum displacement to the right or to the left, that's when it has the maximum elastic potential energy. When the object is at equilibrium, as they show here, that's when it's going the fastest and it has purely kinetic energy. So as it moves back and forth, the transformations take place, and here's what the graphs look like. Once again, at the ends of the travel, you have maximum potential energy. As it goes past equilibrium, in either direction, it has maximum kinetic energy. So the potential energy, when you start out, goes to all kinetic, then goes back to all potential, goes back to all kinetic, back to all potential, and transfers back and forth. We know how you can find the period from a graph, and if you know the period, you can calculate the frequency. But how do you calculate the period and frequency from other equations? We see once again that here frequency is the number of cycles per second. It depends on the physical properties of the oscillator. It does not depend on the amplitude of oscillation. If we look at a spring mass system here again, the properties of the oscillator are the spring constant and the mass. In equation form then, we have these equations for frequency and a period. You can see the frequency is 1 over 2 pi, it's square root of k over m. If you take the reciprocal of that, you get this. It's the square root of m over k. This tactic box for simple harmonic motion let me start over and see if I can say that correctly. This tactics box for simple harmonic motion summarizes what we've said about simple harmonic motion. Simple harmonic motion means a net force is linearly proportional to the restoring force. So if you think about this, the force is a linear relationship to the displacement. That's simple harmonic motion. We've seen the equations for position, velocity, and accelerations and looked at their graphs. A was the maximum amplitude for the displacement. This was the maximum amplitude for velocity. That's the maximum amplitude for acceleration. We saw the relationship between frequency and period. Then if we have a mass on a spring, here's the formula for the frequency. And then we saw that the potential energy and kinetic energy, the sum of those is constant. So knowing that information, we can solve simple harmonic motion problems. Let's now look at pendulum motion. If you take a mass and you put it on the end of a string and you pull it back and let go of it, there will be a restoring force or net force back toward equilibrium. If you draw the free body diagram of the mass in this position, what you see here is the tension is directed along the string. The weight is straight down, and if you break the weight into its components, you get this component, which equals the tension, and then this is the net force that causes the ball or mass to swing back toward the equilibrium position, and this force is equal, or weight, component of the weight, is equal to minus W sine of theta. If we write that in equation form down here, then the net force is equal to minus W sine of theta. And we can substitute mg for that. And this is not simple harmonic motion. Simple harmonic motion says that the force has to be a linear relationship with the displacement. The sine of theta is not linear, it's sinusoidal. So what we have to do is we have to make an approximation here. For small angles, the sine of theta is approximately equal to just theta in radians. If we make that substitution and allow this to happen just for small angles, then this is a simple harmonic relationship. The net force is linearly related to the angle theta. And then we can substitute, looking at the triangle, we can substitute theta here in terms of L and S, the arc length. If you look at this triangle here, S is on this side and L is on that side, and theta is the can be approximated as that ratio as we show here. So the equations of motion can be written as a cosine, or in terms of time and cosine, or in terms of theta and a cosine function. Well, let's look at the frequency of oscillation and the period. Remember, those are dependent on the physical properties of the oscillator. It does not depend on the amplitude of oscillation for small angles. In the pendulum, we call this the simple pendulum, the mass on a string where the string mass is negligible. The parameters or properties of the oscillator are the length, and that's all. It turns out the mass cancels out, and the length will determine the frequency. A G there is a constant. When you look at what we call a physical pendulum, it's a little more complicated. In a physical pendulum, we can't, we have a mass here that's distributed like that. We can't use a particle model. We have to use the rigid body model, and so this rigid body is rotating, and we have to use the moment of inertia in our formulas. So without going through the algebra, what happens is then the physical properties are the moment of inertia and the mass, and d here is the distance from the pivot point to the center of gravity on that physical pendulum. So those are the properties we find in the equation there for the frequency. One comment here: when you make a substitution for the moment of inertia for whatever the physical pendulum is, the mass will end up canceling out of this equation also.